My name is Sam. This is joint work with Seny, Tarik, and Stan. So the problem of building end-to-end encrypted relational databases has become a very important one in database security. It has been studied in the last 20 years. A lot of progress has been made. However, there are still limitations in security, performance, and query expressiveness. So in this work, we would like to call for more collaboration between database and cryptography communities to look at this problem together. And in this spirit, we proposed 5 principles, and we developed the first attempt approach for these 5 principles in the form of new system, scheme, and technique. It's not going to be the final solution. However, we do hope that this serves as a first step for future improvement. The reason we need encrypted databases is to protect data privacy. And as all of you have known, the data has been produced and consumed and constantly enriched in a variety of different ways. So as a result, the data has become more comprehensive and privacy sensitive. On the other hand, it's also become harder to secure, as seen by the constant occurrences of data breach. This has become a problem not only for internet companies, but also for credit bureaus, political organizations, healthcare industry, and many more. So this is a really important problem. So one approach to this problem is to use end-to-end encrypted databases. As a broader concept, end-to-end encryption can be viewed as follows. The user interacts with the server by first uploading an encrypted data. And then the user interacts with the server by sending queries in the encrypted form. The server carries out the computation entirely on the encrypted data and sends back the encrypted results to the user. So in this paradigm, attack can corrupt the server and steal a snapshot of the encrypted data. So this is called a snapshot attack. A stronger attack called persistent attack not only have access to the snapshot, but also the interactions. So in this paradigm, information available to the attackers is conceptualized as leakage. So now let's compare different approaches to encrypted databases. So one is to use generic building blocks such as fully homomorphic encryption and secure multi-party computation and oblivious RAMs. So these building blocks tend to lead to solutions that are inefficient, but can offer very good security. On the other hand, property-preserving encryption, such as used in systems like CryptDB and Wanami, tend to offer very high efficiency, but also very high leakage at the same time. A different approach is to use trusted hardware, but systems use this approach tend to assume a different security model. Lastly, structured encryption based solutions tend to be very efficient and have very low leakage. But at the same time, they only work within key value models. So knowing all of this, how do we come up with the design principles govern the future development? So the first is the minimal leakage. So the solution needs to leak at most the table sizes statically. And for queries, it should leak at most the output-dependent information, so to speak. In terms of efficiency, it should have low asymptotic overhead, in particular, constant overhead over plain text. It should support optimization, which is a very important database technique. It should cover ideally the entire SQL, but at least the conjunctive queries, which is a very important class. And lastly, it should support legacy, which means it should not require intrusive software changes to standard databases, because then it can impose minimal adoption overhead to the service providers. In this work, we strive to cover all 5 principles. However, we made significant progress in 3 of them. Namely, we are able to support optimization and legacy in a structurally encrypted database while maintaining minimal leakage. We use an encrypted multimap as the building block to construct a scheme called OPX. Then we use a technique called emulation to render OPX legacy friendly. We implement all these pieces inside a system called CafeDB. So first, the building block. Multimap is data structure that associates a label with a tuple of values. And on the right, I show you one such example. So get operation, for instance, takes input of label 2 and returns associated values A, C, and D. Encrypted multimaps has a lot of different constructions, but all of them assume the same form. So the user uses setup algorithm to encrypt a multimap and uses a token algorithm to compute a token based on a query, a label, and the server then, upon receiving the token, will carry out the computation directly on the encrypted multimap to extract the result. So OPX is constructed using the encrypted multimap, and it has stronger security than the PPE-based solutions such as CryptDB and Monomi. The new advance here is really the support for query optimization, which is the first time for structurally encrypted relational database. On the other hand, we also offer a new technique called emulation, which solves another open problem for structured encryption, which is legacy friendliness. At a high level, this is how it works. It takes plain text tables and identifies different operations, such as projection selections and joins. And here we'll make a special distinction for 2 things, the partial join and partial select. These are the constructs for encrypted query optimization used later on. So the OPX setup algorithm takes these operations and the tables and represent them in encrypted data structures, such as EMMs and sets. However, these encrypted data structures are custom. They are not recognized by databases. So we need a new algorithm called emulation reshape, which essentially turn them into tables. And finally, they can be stored on unmodified database. For queries, we start with a SQL tree, and it goes through a standard optimizer to become an optimized query tree. For these operations, we know that they all have representations in encrypted database. Therefore, the OPX can use the token algorithm to compute the tokens for all of these encrypted data structures. And as a result, it outputs a token tree. This token tree then go through another algorithm called emulation reform to become a SQL query again. This SQL query can then be run on unmodified database. So all of these are implemented inside a CafeDB system that we propose. And here is the architecture. It has application, client, and database server. The application still uses an unmodified interface, whereas the server runs a unmodified database, such as Postgres. All the actions and complication actually goes in the client layer, and we don't have to mind all the details, but at a high level, it has a front end that parses the query and optimizes the query into a plan. It has a crypto module. You can think of it as the OPX scheme. And we have an emulation module. The high-level takeaway is that the architecture allows a plugin of future improved crypto scheme and the emulation module so that the system can improve based on the independent advance of these modules. Now let me show you the first pass of the evaluation. So the most important one is the encrypted query optimization. Here, selection pushdown has 1 to 2 orders of magnitude speedups. For the entire benchmark of the plain text, it has 2 orders of magnitude slow down and 1 order of magnitude larger in size. In terms of scalability, it's still quite limited. It has 3 orders of magnitude slow down for scale factor 10. So the takeaway is that even though we are able to solve encrypted query optimization for the first time for a structurally encrypted database, but it still needs a lot of work in terms of improving efficiency while keeping the good security. In conclusion, we presented the problem of end-to-end encrypted database, and we presented 5 principles for security efficiency and practicality, and we presented our first attempt solution and outlined the future improvement for efficiency and security and more. Thank you.